Hello and welcome to this Agilent Technologies recorded webcast. We hope you will find this webcast both interesting and valuable. If after viewing this recording you are interested in more, please go to our Agilent TM webcast YouTube channel for more recordings or sign up for one of the upcoming live sessions at www.agilent.com/find/web_seminars. Now let's go over to the presenter.
Welcome to our third webinar series of photonic webcasts. Be ready for 40 and 100G optical networks and components. Our topic today is rating optical signal quality using constellation diagrams. Before going into the details, I would like to give you an overview of what I will go to present in the next 45 minutes. First, I will give you a brief introduction, what is about digital modulation, how does it work, and why do we can get more efficiency transmission than in our standard on-off-key modulation formats. The next part will be the synthesis of advanced optical modulation schemes. Here we will have a look how we can synthesize this kind of signal and what could be the reasons for impairments in this kind of transmitters. And in the main part of our webinar, we will analyze various impairments of these optical transmitters, namely IQ offset, gain imbalance, quadrature error, phase error, and IQ channel delay. And at the end, I will make a summary about what we have learned in this webinar. So let's start with the very basic stuff. So first, what is digital modulation? On the left side, you see an example, a very basic example of a frequency modulated signal. You see below here the original information which is by nature analog. And therefore, the modulated signal is also continuous, meaning analog. On the other hand, the digital modulation on the right side, we have a sharp transition between the two information units, 0 and 1. And this translates also in the carrier in a sharp transition either of the phase or of the amplitude. In this case, I have shown you a sharp transition of the phase. So what does Wikipedia say about the difference between analog and digital modulation? The aim of analog modulation is to transfer an analog baseband signal, for example, an TV signal or an analog passband channel over an analog passband channel. In contrast, the aim of digital modulation is to transfer a digital bit stream, for example, an IP traffic over an analog passband channel. So in both times, we transmit the signal over an analog passband channel, but the nature of the original signal is different. So digital modulation is more than, let's say, just digital modulation, digital on-off. It's a kind of vector modulation. And I would like to explain this concept a little bit in more detail, because this leads us to the reason why we can efficiently transmit the signals over a small bandwidth. So what you see here is a representation of a carrier signal, which is represented by amplitude and phase. Here it is displayed in the polar plane. You can also describe this plane by an X and an Y value, which is called in this case the in-phase or the real part, and the quadrature or the imaginary part. So you can translate this vector between its I and Q values, the Y and the X parts, and the amplitude and the phase. Each of these parameters can be modulated to carry information. So the position of the vector endpoint is called a constellation point, and therefore the diagram is called a constellation diagram. So how can we transmit this kind of vectors? How does this look in reality? Here I have described a transition between two vectors. One is represents as a 1, 0, and the other represents a 1, 1. So the only difference between these two vectors is the phase difference of 180 degrees. Both have the same amplitude, as you can see on this circle. And each of this amplitude, each of this point represents the sampling point of the symbol clock. For example, in this case, the falling edge of the symbol clock represents this point in the polar diagram or in the constellation diagram. When at the next falling edge of the clock, the vector must have this position, namely the same amplitude, as we can see here, but a different phase. In this case, just an opposite phase of 180 degrees. And you can see that in between this symbol clock, there's the switch between the original phase and the phase of the next vector that has to be transmitted. You can see here the I part of the vector and the Q part, how this looks during this transition. So vectors defined by amplitude and phase are separated by the transition of the transmission clock. In this case, we call this also the symbol clock. So how can we code information to a vector? So I have shown here again the constellation diagram for the traditional on-off keying format. On-off keying format is what we are using in the optics since 15, 20 years. And it's just switching the amplitude on and off. And when we represent this on the constellation diagram, we have 2 points. One is the high amplitude, which represents the 1, and the other is the low amplitude value, which represents the 0, and it is ideally 0. So the information that is coded in these two states is 0 and 1. Assuming a pure phase modulation format like BPSK, here the information is coded as already mentioned in the phase, and the amplitude stays constant. Still, we have only 2 symbols available to code with 0 and 1. And last but not least, we can also mix amplitude and phase. And I have shown here an artificial format, which is amplitude and phase modulated. Again, the 1 is represented by the real part, and the 0 is represented by a different amplitude and then 180 degree of phase. So what we learn from here is that modulating amplitude and or phase does not necessarily mean higher transmission efficiency than on-off key format that is used currently in most of optical transmission. So how can we pack information more densely? On the top of the slide, you can see an arbitrary bit data stream. So how can we reduce this amount of data? We can reduce this by coding. For example, we can pack together two of these bits to another symbol alphabet that we call arbitrarily, for example, A. And then a 1, 0 is a B. And so we can code all 4 states in the 4 symbols A, B, and C, and D in this 4-symbol alphabet. But we can code, we are free in coding, and so we can code this also in another way. We could, for example, use the 0, 0 and code this as an A times sine omega t plus 45 degree. And we can code the 0, 1 as A sinus omega t plus 135 degree, and so on, coding the 1, 0 with 225 and 315 degree. So in this case, we are increasing the number of symbols that are coded in an alphabet, and this increases the number of bits that can be transmitted in one clock. And this is a very basic concept of advanced optical modulation formats. And now I would like to go back to our first introduced constellation diagram. And I have represented these 4 coded vectors in this constellation diagram. And you can see here each of the 4 vectors and the corresponding bit sequences that relate to these points in the constellation diagram. And we transmit these vectors by transmitting the corresponding modulation, either 45, 125, 35 degrees, and so on. So a 4-symbol alphabet codes 2 bits in 1 transmission symbol clock cycle. So this leads to an improvement in the spectral efficiency by a factor of 2. One other word regarding the relationship between transmission rate and symbol rate. So here you can see again in the middle an arbitrary original data stream, which is represented by 0s and 1s, and the corresponding data rate clock on the upper part of the slide. Again, if we code this to a symbol like A, B, C, D, we only need to transmit 4 symbols. And this is very clear then that for transmitting only 4 symbols, it is sufficient to transmit this with half the symbol rate, as we call this in this case. So in this special example, the data rate would be twice the symbol rate, or we have reduced the needed bandwidth by a factor of 2. And this is, again, the reason why advanced optical modulation formats or advanced modulation formats are so attractive in RF, but also in the optic world. So symbol rate or baud rate describes the symbol transmission clock rate, not the transmission data clock rate. And again, if we can extend this concept, for example, we could code a 16 symbol alphabet with combining 4 bits. In this case, we would get to a 16 order QAM format, and of course, this can be extended anymore to QAM 32. Even it exists in RF QAM 1024. So the symbol rate in the QAM 16 is 4 times lower than the clock rate. So this means, in addition, not only saving in speed, but also saving in power, because the higher the bandwidth of your electronics needs to be, the more power it consumes. So this is the first part. I would like to summarize the most important points here. Digital modulation transmits information as a vector defined by amplitude and phase. Information is transmitted with higher efficiency through coding of vector positions to a bit sequence. And the position of the vector in the 2-dimensional polar plane is called a constellation point. And the arrangement of these constellation points is called a constellation diagram. So now let's have a brief look at the way how we can synthesize this kind of signals. So here I have outlined the basic structure that is used in RF and in optical modulation to create an IQ signal or an in-phase quadrature modulated signal. At the entrance of this transmitter, you see here the original bit data stream. This goes to a 2-to-1 switch, which switches with a symbol clock between the in-phase path and the quadrature path, leading to this new data stream that is the divided one between the original data stream. At the beginning, you have typically an amplifier on both paths, and then you go to the original modulator that modulates your carrier. Here you can see the carrier. The carrier is fit to both modulators, but on one part of the signal of the transmitter, the carrier is phase shifted by 90 degrees. And here you can see the corresponding constellation diagrams of the signal in between this transmitter. You see here the in-phase modulation just carrying the real part of the signal, or 180 degrees, and the same constellation diagram, but rotated by 90 degrees, you can see at the quadrature modulation path. So if you combine both of them, you will end up in this constellation diagram that has 4 constellation points, and to these 4 constellation points, as we have seen before, you can code 4 bits or 2-bit combinations. So the IQ modulator codes a data stream into a vector stream. So how does the optical IQ or vector modulator look like? And I have here a basic outline of this. Of course, it has the same structure. We have at the beginning our data stream with a multiplexer to the in-phase and the quadrature path. We have our driver amplifiers for the modulators. And in the optical world, the modulator are represented typically by a Mach-10 interferometer on the in-phase and on the quadrature modulation path. Now we need, in addition, the 90-degree phase shift part, and this is also mostly realized as a Mach-10 interferometer, which is biased accordingly. So then we have again in the in-phase path here our constellation diagram that we all know, and in the quadrature part we have the 90-degree rotated constellation. And at the output of the transmitter, again, we have the sum of these 2 constellation diagrams representing 4 points in the constellation diagram. So the optical IQ modulator has the same structure as any RF IQ modulator, and this is very natural because what we are doing is here, this represents the basic mathematics between this modulation. So what are the possible impairments of an optical IQ transmitter? I will outline here only the most obvious ones. Of course, this is I have no claim that this is all what could happen in this kind of transmitters. As we have 2 paths here, the in-phase and the quadrature path, of course, there could be a gain imbalance between these 2 amplifiers, for example. We could have also a path delay difference between the I and the Q channel. We could have a wrong setting of the 90-degree phase shifter. And we could have several kinds of influence of the line width or the phase noise of your carrier generating laser. And in addition, there could be an offset between the symbol rate, between the receiver and the transmitter. So the question now is, how can these impairments be analyzed? And how do they distort the constellation diagram? Are there special patterns that lead to a distinct error? Are there tools available in addition to the constellation diagram? So to analyze this kind of signals, we need to go into more depth of this analysis tool. And I will show here, based on these examples, how various how to look at these signals might lead faster or slower to the possible error root cause. One instrument how to do this, and my analysis here is, of course, based on this new optical modulation analyzer that we have introduced at the OFC this March. And this tool is to analyze the transmitter during design phase and also in manufacturing. It offers the constellation analysis, but besides this, it offers also spectrum analysis, eye diagram, display of I and Q paths, the error vector analysis of magnitude and phase, and other related analysis tools. I will explain in more detail later on this error vector magnitude concept because this is very well known also in the RF world. In addition, this instrument offers a scalar constellation description to be able to rate your quality of your constellation diagram and much more advanced analysis tools. So now let's go to the hard facts. Here I have shown a constellation diagram with a distortion which has an amplitude distortion in the in-phase path. And you see here at these cross points, they represent always the ideal position of the constellation points. Ideally, you have only one point at each constellation and not this kind of cloud. Of course, the reality is not ideal, so we have some noise, and this cloud represents the noise of our system. So, how could we qualify this kind of distortion? First, we look at our standard tools that we have been using in former times, which is mainly the eye diagram. With the instrument, we can, for example, look at the eye path and the Q path of the eye diagram. And you see here again the distorted constellation diagram. And you can see here, as we have here in both axes the same scaling, that there is a different amplitude of the I and the Q eye diagram. So this leads to the indication that you have a gain imbalance, and the instrument directly shows you that the gain imbalance here is at about 2.9 dB. The gain imbalance is defined by 20 times log base 10, the ratio between the I and the Q amplitude. So this kind of distortion, the IQ imbalance, the gain imbalance, describes the gain imbalance between the I and the Q path of the transmitter. Here's another kind of distortion. If you have a first look at this distortion, you might think also this is related to a kind of imbalance or amplitude imbalance. As you can see here, the vector they have different amplitudes, and they are clearly orthogonal, and this could lead you to a wrong assumption. So let's go to the next step of the analysis. Again, we look at our already known tools we have available. Here's again our constellation diagram with the ideal constellation points and the distortion here. And we see here the I diagram of the I part and the Q part. And what we see here is the I has, there's some jitter. There's the eye is not well opened, and you see there's something wrong. But comparing again the same scaled amplitude of these two passes, we cannot see any kind of imbalance as we have been seen in the example before. So what we could also use, we could use a high-resolution spectrometer, as this is also included in this analysis tool of the instrument. But also here we cannot see any significant pattern that might lead to the possible error. So if we have a look at the scalar analysis tools from this instrument, for example, again, here is our distorted constellation diagram, and here is the corresponding analysis that is provided. And we can see here that we have a quadrature error of close to 20 degrees. So this means, in fact, that our phase shift is not 90 degrees as it should be, but it is only about 70 degrees of phase shift. So this is the reason for this distortion. And if you see this kind of distortion, you can directly go to your bias voltages of this Martin interferometer and adapt your and optimize your transmitter to have a perfect constellation and 90 degrees as it should be between the I and the Q path of the signal. So the quadrature error describes the deviation from orthogonality of the I and the Q modulation. Another offset that might occur during the design of a transmitter, for example, is the IQ offset. The IQ offset simply describes the offset of the constellation diagram from the origin. Again, the cross points are the ideal points, and here we see the measured squared constellation diagram. In this case, the instrument measured minus 31 dB of IQ offset. Just to give you an indication, what would be a very good value is minus 60 dB. And the reason for this IQ offset is typically a DC offset in either I or the Q path. So now we have looked at the various imbalances between the I and the Q path and the misalignment in the P half phase shifter. And now let's have a look at the influence of the quality of the transmitter laser of the carrier creating element. I have shown here you two examples. One is an DFB source. This is a high resolution spectrum of the DFB source used in this case. And in addition, I have shown an external cavity laser, which has a very low line width of about 100 kilohertz, in contrast to the DFB laser, which has a line width of typically 2 to 3 megahertz. So the question here again is, how does this difference influence the constellation diagram, or does this even influence the constellation diagram? So again, I would start with the traditional test tools that we have available. This is the I and the Q. And again, here we can see there's a higher jitter. There's a not very open eye. But this is all we can analyze from this kind of signal representation. And also, again, the scaling is the same. So although it looks to be not an imbalanced path of the I and the Q part. Also, again, a look at the high resolution spectrum gives no indication to the error of the source. So the right tool can give you the right answer. And here I have shown you the corresponding constellation diagram that can be seen if you use a DFB laser as a transmitter. If you look at the constellation diagram, you can get the first indication that phase error might be the cause of this distortion here. So you might be aware in the constellation diagram, this direction represents the phase, whereas the distance to the origin represents the amplitude. And here we can clearly see that there's a noise, a phase noise present in the transmitted signal. In contrast, here we have a very good transmitter. Of course, it is not perfect aligned, but we see here a Gaussian distributed, a kind of Gaussian distributed noise. And if we look at the phase error of this signals, we can get the proof that we really have here some unphase error. Here the red phase is displayed above on each symbol or versus time, and you can see that we have here a deviation of the ideal phase error from 0. In contrast, you see here the phase error of this signal, which is close to 0, just with some Noisian deviations. And this is the same transmitter, just using an external cavity laser with a line width of, for example, 100 kilohertz. So you can see the transmitter has significant, or the transmitting laser has significant influence on the performance of your transmitted signal. So I think now it's time to introduce the error vector concept. Here again, we have our constellation diagram as already described at the beginning of this webinar. You can see here again our ideal constellation point represented by the amplitude and the phase of the signal. But the world, as we all know, is not perfect, and we would probably measure this constellation point instead of this point. So we have here an error vector which is described by the Euclidean distance between the symbol coordinate and the actual recorded or measured coordinate. For example, the error vector magnitude is part of the 802.11 WLAN standard. So this is just an indication that this is a very well-known concept in the RF world. So how can we create this error vector? So we have only the measured signal available, but which goes in there. But we can, or we do demodulate our test signal, and then we have our decoded bit stream that is shown here. This bit stream we can filter, and then we can get a kind of reference trace represented here as this eye diagram display. And from this trace, again, we can reconstruct our I and the Q signals, leading to an in-phase reference signal and a quadrature reference signal. These two signals can now be used to compare with the original measured signal, and this exactly leads to our error vector. And we can use, if we have both of these signals, we can make additional error analysis tools based on these two kind of signals and look in various ways on our transmitter signal. So what can the error vector magnitude tell us about the transmitter? So I have here shown 3 examples of a transmitter we partly already discussed here. The first transmitter is a very good transmitter, well aligned with an external cavity laser, and what we can see here easily that we have a kind of white noise distributed error vector magnitude. This error vector magnitude is calculated to a value of close to 13%, which is a normalized value. In addition, if we look at the error vector magnitude diagram here with a phase distorted constellation diagram caused by the DFB source, we can see here a noise that is structured and that is not even white. And again, we would probably expect that this slightly imbalance in the gain would not reflect any structures or any impairments in the error vectors. But if we again look at the error vector magnitude here in this diagram, we can see some dominant structures like a kind of V-shapes in this diagram. And in both cases, we see an increased error vector magnitude of close to 35 and 33%. So what we can conclude from this, in a well-aligned transmitter, free of impairments, the error vector magnitude should be white noise distributed, and the percent RMS value should be as low as possible. Here I have brought you another very distinctive EVM structure. We can see here the constellation diagram that has very structured constellation points, but even well centered around the ideal points. Looking at the I and the Q part of the eye diagrams, we can see there's something not perfect in the transmitter, or even very imperfect. And when we look at the error vector magnitude, we see here a very pronounced strong V-shape. Here again, we see the symbols aligned that we are analyzing. So the eye diagram gives no clear indication, but indicates a problem. So, and what is the reason for this problem? So this problem, this V-shape, this very pronounced V-shape, is caused by a slightly wrong symbol rate between the transmitter and the receiver. So you see here the symbol clock producing the two data streams, and in the receiver you need to input the used symbol clock to either to the instrument or to your real receiver itself. And if there's a slight misalignment between these two symbol clocks, you get a kind of fading that is represented by the different periods of the actual symbol clock and the sample symbol clock that leads to these errors described here, and this leads to this pronounced V-shape of your error vector magnitude. Again, if you see this kind of V-shape, you could get an indication that your symbol clock is not well entered in the system, or there's something, for example, unstable in the symbol clock. If you see these shapes only partially appearing on the screen, for example. So small errors in the symbol rate cause a typical V-shape in the error vector magnitude display versus the detected symbols. And again, another kind of impairments that we didn't discuss up to now is the delay of the between the I and the Q path. Up to now, we have mainly discussed the gain imbalances and other impairments, and now we look more at the timing between these two signals. So what we can see here at the constellation diagram that was measured with a delay that is below a symbol length, and we can see here a very characteristic open of these transitions. And also here on this side we can see this opening in the transitions. And this opening is caused by the delay between these two channels, the I and the Q channel. So the small delay between these two channels look like a bandwidth limited modulator driver. So the question is here, what is the root cause of this, or why does this look like a bandwidth limited signal? And we can even think that a delay between these two symbols, between these two transitions or let me say it in another way, a different bandwidth causes different group delay, and the group delay implies that there is a different traveling time between these two paths, and this indeed is exactly a difference in the symbol positioning of these signals. So last anomaly I would like to present, which is also very interesting. We have here a constellation diagram with very good constellation. We can see here the ideal representation, again with this crosses, and we see here the constellation centered around this crosses. We have here used a short PRPS of a length of 2 to the power 5. And again, we look here at our eye diagrams, and we see here very good eye diagrams of the signal. Also, looking at the error vector magnitude indicates a wide nose. So based on what we have learned up to now, there's no indication that there might be a problem with the signal. So if you look at different times to the signal, so namely looking at the transitions, not only the constellation points, we see here in the lower part of the diagram, we see just the constellation points, and here we say, in addition to the constellation points, we see the transition between these constellation points. And what is very interesting here is that there's no transition between these points. All transitions go via different vector positions. Again, the eye diagram gives us no indication about the root cause of this view behavior. And here's an explanation of this delay, of this impairment. Here we have used a 4-bit delay between the I and the Q path of the signal. So the original I signal would look like this. For example, this is just an arbitrary bit stream that we have here, the original data stream. And then we have the original data stream at the Q path of your transmitter. And now we assume that one part is delayed by 4 bits, which I have represented here. And then let's take a look at the constellation diagram. The original constellation at this point should be a 0, 1 to a 1, 0. Here we have the 0, 1 and the 1, 0. But when we shift this, in this case by 4 bits, for example, then this translates to a 1, 1 to 1, 0 transition, which represents this kind of transition. Here's the 1, 1, and here's the 1, 0. So assuming that the PRBS is quite short, it is not long enough to play with all combinations in combination with a 4-bit delay, and this can cause this kind of distortion or misalignments in the signals. And if you want to test your transmitter at all transitions in all points, this might be important to know, to look also at the IQ, that you really get all the transitions during your tests. Again, this is especially the case for very short PRBS sequences. So now I have shown you an overview of the major impairments that could arise when designing a transmitter or, for example, during manufacturing. And I would like now to make a conclusion what we have learned about these examples I have shown you that were measured with this new instrument. The quality rating of a transmitter operating with advanced modulation formats is more challenging than on transmitters that operating just with on-off keying. And you can imagine that this would be even more critical or even more challenging if you would use higher order modulation formats like the 16-QAM as shown at the beginning of this webinar. Also, the constellation diagram analysis gives significant more information about the signal quantity that is emitted than observing just an I and then a QI diagram. Being able to know a specific pattern of the constellation diagram often leads also directly to the error source. We have seen this very pronounced in the case with the quadrature error, where we had a very clear pattern of the distortion of the constellation diagram, for example, and this led us direct to the distortion or to the misalignment of the 90-degree phase shifter in the Q arm of your transmitter. Additional analysis tools based on signal error analysis like error vector magnitude or phase error lead to more advanced debugging capabilities. So we have seen this at the example of the error vector magnitude. This showed us more details about the signal, and also looking at the phase error can give us an indication how well our transmitter laser is working, for example, and how well we can get a transmission, which leads at the end to a low bit error ratio. The ability to quantify various constellation characteristics makes this an ideal tool for specifying the quality of the transmitted signals. You have seen during this during various examples that I could really name the values of the distortion. For example, we had also the quadrature error with nearly 3 dB of error. And with this color description of the constellation diagrams is a very powerful tool to describe the performance of your transmitted signal, either in the lab or for specification of the transmitter, for example. So now I have shown you several examples of impairments that could influence the constellation diagram, and I have shown you also the root cause of this, and all these examples were measured with an optical modulation analyzer. And if you would like to have some more information, you can look here at our web pages. And in addition, I would like to highlight also our white paper that you can find on this web pages, Methodology of Advanced Optical Modulation Formats. There we describe in detail the 3 basic concepts how you can measure this kind of signals and compare them with advantages and disadvantages. If you are interested in more basic knowledge about digital modulation, we have also an introductory application note that you can find on this link. And finally, if you would like to see the instrument live, please join us at the ECOG 2009 end of September in Vienna. At last, I would like to again highlight our 2 digital and photonic webinar series that are continuing out of the year and next year. One series is Master the High-Speed Digital Test Challenge, and the photonic webcast is Be Ready for 4000G Optical Networks and Components. So thank you very much for attending this webinar. And I think we are now open for questions. Thank you very much.
Great, thank you, Oliver. I do know that Bernd did receive at least a couple of questions. Bernd, if you want to take the floor, and if anyone has any questions, please feel free to chat at any time.
Okay, thank you. So the first question maybe to Oliver is, are all measurements shown coming from the Agilent N4931A optical modulation analyzer?
Yes, of course. All these measurement tests were done with a transmitter here in our lab and with our instrument.
Okay, I see a second question. In the RF world, the bandwidth of the modulated signals can be controlled by applying a filter to shape the transition. Does a similar method exist in the optical world? Is it important to have it?
Yes, in this instrument also exists this method. You have the possibility to equalize your signals for better performance of your measurements.
Did you receive any other questions, Bernd?
Not in the moment.
Okay. If anyone does have any questions, please feel free to chat. If you do think of questions after the event, please feel free to email Oliver directly at oliver_funke@agilent.com. And just a reminder that you will get a short feedback form that will pop up once the WebEx interface has closed. If you wouldn't mind just taking a moment to fill that out, it would be greatly helpful. If there are no more questions at this time, we will end.
I think there's another question.
Oh, perfect.
Why do you think the error vector magnitude is superior towards bit error rate test? Because in optics, when communication bit error rate test is widely used.
Yes, let me go a little bit deeper to explain this, because bit error rate just displays you the error of the detected signal. But assuming you have a very good transmitter and you're measuring at the output of your transmitter, you will get probably a zero bit error rate because you have a very good signal to noise ratio, which represents a low error vector magnitude RMS percentage range. So, but if you think about the Gaussian distribution by calculating the bit error rate from the error vector magnitude, assuming the Gaussian distribution of your constellation points, you can still calculate, like with a Q factor, you can calculate the bit error rate from the error vector magnitude. And this is the reason why we think that this concept is very powerful.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. Remember, all our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcast and to sign up for free, go to our website, www.agilent.com/find/web_seminars.